about simulating a dipole antenna in HFSS. So if you have HFSS, you can simulate a dipole antenna, student version of HFSS, or in the department you can use HFSS to simulate a dipole antenna. So we discuss about how to simulate a dipole antenna. Now before we do that, I want to tell you something else which is not related to simulation of dipole antenna, but an experiments that you can perform in a virtual lab. That again is a simulation. So the experiments that are prescribed to you for your first semester or all the semesters, the experiments that are prescribed, you can do them in the virtual lab of IIT Kharagpur. The virtual lab is right now open, and it is open to everybody free of cost. There is no cost attached to do the experiments. You can visit this website. The website at which you can do the experiments, virtual lab experiments, is this. Yesterday I have given this also to you in your classroom. In Google Classroom, this website is available. You can follow this website. Otherwise, those who have not read or those who have not received the information, those who are not on the Google Classroom, they can see this. This is the website vlabs.iitkgp.ac.in/vlt/project.html, and you go to this website. There you can perform different types of experiments. Start with the basic experiments, which is the fundamental experiments that are there. Our basic electronics lab is there. Go to that lab, do the experiments. These experiments, when you do these experiments, everything is there. What is the theory? What is the procedure of conducting those experiments? So everything is there. If it is not possible for you to do the experiment in the classroom, when we are in the class, in the department, if you are unable to perform any experiment, and those experiments are available at this website, do these experiments. So you will learn about the experiments. You can play with these experiments. Try this out. So with that, let us come to the simulation. What we will do is, we will do the simulation of a dipole antenna, half-wave dipole antenna for the GSM 900 band. So EGSM 900 band, for that band we will design a half-wave dipole antenna. So this is the band, commercial band is called EGSM 900 band. In this band, the uplink, that is from the link which you are sending. So from your antenna you are sending something, that is the uplink, and to your antenna you are receiving something, that is downlink. The uplink frequencies are 880 to 915 megahertz. So the band over which the uplink works is 880 to 915 megahertz. The downlink is 925 to 960 megahertz. This is the downlink. Now, why there are two links? We can have only one link, 880 to 915 or 925 to 960. As you know, if the transmitting signal and the receiving signal are in the same frequency and they are following the same path, in the same path, if you have a transmitting signal and a receiving signal, or a forward propagating wave and a backward propagating wave, these waves will interact with each other. There will be interference. That is possible only when the frequency is same. If interference is possible only when the waves or signals are of the same frequency. If the frequencies are different, there will be no interference. So uplink and downlink, if we go for an uplink frequency, a separate downlink frequency, then the uplink and downlink interference will not be there. That is the main reason for two different bands, one for transmission, one for reception. So one for uplink, one for downlink. Now the center frequency of these two is the lowest frequency is 880, highest frequency is 960. So therefore 880 plus 960 by 2 is the center frequency. That is equal to 920 megahertz. So we should design an antenna which is resonating at 920 megahertz. If it is resonating at 920 megahertz and it has sufficient bandwidth, then using this antenna we can use the antenna for the uplink, we can use the antenna for the downlink. If it has sufficient bandwidth, which means it resonates at 920 megahertz and it works from 880 to 960 megahertz. So that is why we designed the antenna at the center frequency, which is 920 megahertz. If we know what is the center frequency, then we can find out what is the wavelength. Lambda is equal to C by F. Now let us calculate wavelength in terms of millimeter. So lambda is equal to 3 into 10 to the power 11 millimeter per second. You know, 3 speed of light C is equal to 3 into 10 to the power 8 meter per second. That is equal to 3 into 10 to the power 11 millimeter per second. And 920 megahertz means 920 into 10 to the power 6 hertz. So 920 into 10 to the power 6 will be in the denominator. In the numerator we will have 3 into 10 to the power 11. So if we do that, that gives us 326.087 millimeter. That is lambda. Then once we know what is lambda, what is the wavelength, we will find out what will be the diameter of the antenna, dipole antenna that we are going to use. What will be its diameter? Diameter D is equal to lambda by 20, approximately lambda by 20. So let us, for this design, let us take it as lambda by 20. It should be much smaller than lambda by 10, so we are taking lambda by 20. So if we take that lambda by 20, that is equal to 16.3 millimeter. That is the diameter. Then when we design a dipole antenna, we have two arms. Between the two arms there is a gap G. So this gap between the two arms G is equal to D times 0.5. Let us take a small gap which is equal to D into 0.5 or D by 2. That will be equal to 8.15 millimeter. That is the gap. Then dipole length of the dipole, since it is a half wave dipole antenna, so its length will be lambda by 2. So dipole length H is equal to 0.5 into lambda or lambda by 2. That is equal to 163.02 millimeter. Then when we do use a HFSS, we have to use something called a radiation box, a rectangular box around the antenna. So that is what is called a radiation box. So the radiation box size will be Bx. B stands for box. So along X direction it is Bx, along Y direction it is By, along Z direction it is B. So radiation box size is Bx, By, Bz. Bx will be D plus lambda by 2, By will be D plus lambda by 2, and Bz, Z is the direction along which the antenna will be oriented. Therefore Bz will be H plus lambda by 2. So whatever is the size of the antenna, the extension of the antenna, that plus lambda by 2. So radiation box size will be this much in terms of mm. Now you can see, let us see the antenna. Antenna is shown on the right hand side. So we have two arms, the upper arm and the lower arm. For the upper arm, total length is L. Between the two arms gap is G, and upper arm from the center to the upper arm length is L by 2. from the center to the lower arm length is L by 2. Antenna is oriented along Z axis, so you can see antenna is oriented along Z axis. The upper arm extends from a distance of G by 2 in the upward direction. Similarly, the lower arm extends from a distance of minus G by 2 in the negative Z direction. So this is the antenna structure that we will do in the HFSS. Center position, now look at this. The center position is 0, 0, G by 2. Center position for the upper arm, that is 0, 0, G by 2. Axis is Z, along Z axis. The upper arm is oriented. The radius of the upper arm is D by 2, because D is the diameter of the arm, or diameter of the dipole is capital D, so radius is capital D by 2. Length of the upper arm, that is total length, is L by 2, so only the arm length will be L minus G divided by 2, or L by 2 minus G by 2. That is the length of the upper arm. Now let us come to the box, radiation box. Look at one of the corners of the box. Take the position of the box, that will be minus Bx by 2 minus By by 2 and 0. That is the box corner point, that is the reference point. So first fix a reference point. Reference point for the box is minus Bx by 2 minus By by 2 and 0. How you choose it? Look at the XY plane. On the XY plane, look at the lower left corner. So lower left corner on the XY plane is minus Bx by 2 minus By by 2. Because along X, length of the box is Bx, along Y, length of the box is By. So the lower left corner, the lowest left corner is the reference point that we take. So minus Bx by 2 minus By by 2. For the Z direction, we are taking at the center, is the center of the coordinate system is coinciding with the box, therefore it will be 0. Along the Z direction it will be 0. So the box is minus Bx by 2 minus By by 2 and 0. That is the position of the box. For the radiation box, this is the position. Now open your HFSS. First thing is open your HFSS. You will see a screen like this. Here it is written project 4, it can be project 3, project 5, anything depending on your software, how you have loaded it, which project you are starting, it will show you this project. So project 4 or project 3, etc. that will be it. So open this first. And then click on the Insert HFSS Design icon. So I have shown you the icon here. Click on that icon. Click on the Insert HFSS Design icon. So click on that icon. Once you click on that icon, it will show you HFSS Design. Within bracket, differences, all these things. So first it will show you HFSS Design, and you will get a window, small window, which shows you coordinates, then planes, then list. Those will be written there. Once you click on this icon, the icon I have shown, the top left corner icon, that you have to. Then you have to look at the main pan. In the main pan, you will see the axis of the x-axis, y-axis, and z-axis. Rotate these axes using your mouse and orient the z-axis in the vertical upward direction. Then click on the project. Go to project. Once you click on the project, there will be a drop-down menu. On the drop-down menu, select project variables. So whatever is the variables that we are going to use in the project, that we have to define. So select project variables. So click on that project variables. This window will come. On this window, click on the add. That you can see on the bottom, there is a red box which is add. So click on the add. Once you click on the add, this window will come. So we are going to give the length of the antenna. Length, width, all these are length. Length, width, diameter, all these are in terms of dimension, these are all length. So first choose length. So unit type, in the unit type choose length. Name is L, length, choose length. Then put the value. L is equal to 3 into 10 to the power 11, so 311 divided by 920 is 6. So that is the length. That is actually wavelength that you are going to find out. Wavelength. So here you can see unit is mm. So if it is not mm, then you select that unit and make it mm and put it as a variable. So name is L. On its side it is written variable. So click that. If it is not selected, select that. Then come to unit type. Unit type it is L is length. Then unit is mm. So once you do that, then you click OK. Once this is done, then you click OK. So once you click OK, it will show you this $L. Then the value will be shown. This unit will be shown. Evaluated value will be shown. And description you can give as wavelength. L is wavelength. That is the description. And then come to the second one is D, diameter. So D value is 0.05 L, 0.05 L. So 0.05 star of $L. So that is the value. Automatically it will take it in terms of length. Then OK. Next. Then G is equal to D by 0.5. Sorry, D into 0.5. So $D star 0.5 will be the value. Then click OK. Then H is the length of the dipole. Length of the dipole is lambda by 2, therefore 0.5 star $L. So that will be the length. Then Bx, length of the box that we have defined, B plus 0.5 star A. And By again D plus 0.5 star A. And then Bz is H plus 0.5 star A. So now these are all defined. Then choose OK. That is shown here in the bottom. A red mark is given. A red box. Click that. So all the variables are defined. For the project, all variables are defined. And then we will draw a cylinder. So click on draw cylinder. That I have shown you. So click on draw cylinder. It will draw a cylinder, arbitrary cylinder. Once you click it, it will show you how to draw cylinder. So draw a arbitrary cylinder. And then click on cylinder 1 in the command window. Look at the command window. In the command window, click on cylinder 1 and make a double click. So it will show this window. Once you come to this window, then you change the value. Name you can change. Name is written as pole 1. So write pole 1, etc. So make the changes that I am showing here. These changes you have to make. Which one? What's your back? Back. So first choose here copper. The arm is copper, therefore choose copper here. So what we'll do is we'll take a break here. When I come back, then we'll start. I will explain.